know the basic data types and data structures of R, and some of the syntax of it. But to use it as a program, or probably for especially for programmers, what they mostly care is the logic uh, of the system. Now, I've mentioned above that R is a Turing complete machine. Now, so it has loops and judgment. Now, basically, you have loops. Uh, there are different kinds of loops you can get. The most common way of doing loop is using for loops and while loops, and some and but it's worthy to know that sometimes you are creating an invisible loop within some other functions. For example, apply, or let's use parlapar, which is parallel version of apply functions, and you could write loops. You could write loops inside a function, or you could go recursive functions, which serve a similar purpose. But essentially, they are the same thing because they are trying to encode some patterns over and over again, and you could argue that they are not very efficient because um, when you try to say about the efficiency of the loops, judgments, and something we often talk about how many steps does it take to calculate certain thing, and R doesn't need a compiler to run, but it doesn't means uh, you could uh, just not care at any time. But mostly in most cases, you don't have to worry about the efficiency. But it's worth it to know that the for loops in R are not that efficient, and some text processing thing are not very efficient. Now, the one way of avoiding these are using vectorizations, so that you could go some, they call it embarrassing parallel calculation, which is using multiple cores of the computer chips to for let them calculate something at the same time, so you could get some promotion in efficiency, and most importantly is speed. But the the most common way we use for loops for some index in some vectors or a sequence. Uh, let's just call it my sequence. I used this uh, bracket, and there we go, statement statement 2, and so on. So let's just do an example. I think in the last video we mentioned about Fibonacci sequence, so we will do one example about that. Fibonacci sequence, right? So I got, for example, I want to generate a Fibonacci sequence with length 20, say 20. Well, now what I'm gonna do is the first element is to run that. Oh, and actually before working on this, it's better to clean the global environment. You could click on this, or you could go remove things in RS, which clean all the things for you. You don't have to worry about that. F1 and F2. One. Run that. Object F not found. Okay, I think we cleared all of that, right? No problem. So now we're gonna use our for our index in. Let's say we already got 2 terms of this, so we could start with 3. This is the sequence from 3 to the length of f, which is 20. You could put 20 here. So fi, I is just the index. So whenever you use this for loop, I goes from the first term of this sequence to the last term of the sequence. It goes for all of it. So it goes 3, 4, 5, 6, and it's calling the third time of the f, 4 times fourth term of f, fifth terms of f at each time. And I want f correspondingly, right? This is 1 less term than f, 2 less term than f. You could write a lot more complicated for loop than this one. And then you get f. What's f? Yeah, it turned out nicely. Now, while loop, we better to. This is generated by a while loop. I also want 20, right? And while I is wait we better start with something. For example, I want I is 3. It starts with 3. Well, this I is a single variable here, and we don't even need a sequence in while loop, because while this statement is true, it's gonna run the statement over and over again. Alright? While it is smaller or equal to 20. And this is pretty similar. Yeah, I'll just go copy and paste. Great. There we go. But note that because it's a single variable and there's no for I in some sequences here, you should always, after 1 term plus 1, so it goes 3, and then 4, and then 5, until it gets to 20. And 20 plus 1 is 21, which is not true for this statement. This is going to be a false. And I want to make clear here. Actually, this is are generated by while loop. Alright, and we want to make clear that this one is not a statement. This one is something in the sequence. It's gonna call first term, second term, until it goes to the last term. And this sequence doesn't have to be numeric. For example, we could go for our index. Index could be have other name. It doesn't have to be I. Our index in Now I'll give it some characters. It does not have to be be numeric. Numeric. Yeah, I got print our index. Now what do we get? It does not have to be numeric, so it's looping through this vector consisted of characters, and it just works. And it could the statement doesn't have to be calculations. It could be plotting, pointing, regression, lots of things. Now let's get back to this while loop and see if that works well. 3. No, it's now it's looping. Is it working? It's taking some time though. It's 3. Now whenever you get this mark, R is telling you could give it another statement. If it doesn't turn out to be this one, it is probably working. And well, let's just see. It's probably some loops here, but we could always inspect this by just typing it into the command windows. Oh, it seems that it doesn't work. Why is that? Because we didn't tell him the first term is 1, the second term is 1, is it? It's indicating it's a Fibonacci class, but it's not a Fibonacci sequence. So we do have to go from 1 to 2, variables equal to 1. So it doesn't, it doesn't seem to be a legal way. Okay, it doesn't work like that. So what's going on here? While loop. So I have to use control float. While condition. Repeat. Break. Next. Okay. For loop. It doesn't matter. While loop. There is some problems. For while this is smaller. What if we go this is smaller than 21? No. It's not working. Oh, it still turns out to be 112000. I don't know what's going on there. Guess in most cases we use for loops for some reasons. Now, this there is some reasons that this one doesn't turn out nicely. Now it's gonna run this statement over and over again until this one turns out to be false. Now, you go this one, and then I see what's the problem here. We must assign I to I plus 1. Now here's what's different from mathematics. Well, to prove that I'm not lying, let's just run this code, and I guess our while loop generated Fibonacci sequence, which is identical to that. Right. This is quite different for mathematics and computer programming, because when you get a math, this is not gonna work. But if you put in computer, well, actually, you could go equal sign here, or just make sure there's one equal sign, and you run this code. I actually want to run this, and it turns out to be the same answer, because one equal sign means it takes the value of the right side and give it to the variable of the on the left side, or you could use this assign syntax. This works. Now this is for loops and while loop. But there are more things you could do with it. For example, I want the next term divided by the previous term, and I want from 1 to 20, and it's gonna give me 19 answers. And let's just remove. We don't need that. Okay. Let's just example over 2. Division by term. Well, actually, we should call this the previous term, the one term divided by the previous term. Now, we get an f here for I in f. We want to give it. I want to define something like d is numeric 19, and this for I in f. You could go C colon, or just no. Actually, we want something from 1 to 1 length of f minus 1, so that it goes through 1, 2, 3, 4, 5 until it gets to 19 and stop. So our term I of d, we assign it to a value, which is the I plus 1 term of f divided by the ith term of f, and it's gonna give me the divisions. This is right. This is how for loops works. And what's important about this code, if you run d, well, this of f, right. So what is f? Okay. Yeah. It should give us some 19 something consists of 19 terms. So which means we probably made a mistake. F. Well, no problem about F. I want the ith term of D to be F. Well, actually, it's D a function. Divided by F5. Yeah, that's 1 2 15. Sorry, 1.5 something, and you could visualize it very easily by using plot seek along. I like using seek along. D. Yeah, what do we get here? Now it seems that our new sequence converge at 1.618 something. Does it remind you about the golden ratio? Let's just say there's some value equal to 1 plus square root of 5 divided by 2. There we go. Now, we could, to make it nicer, we could go ep horizontal equals to this value. You know this is called phi. Here we go. This is our plot. Now this one doesn't seem to be a problem, but if you get some larger value, let's just actually do this Fibonacci sequence for some larger values. Now, for some larger sequence, as this. Well, actually, this is for sequences which involve more calculations. Now we gotta have this, but instead of getting 20, I want, how many is that? Now, we could get F very easily, but here's some problem. What's the time it does to just take to generate all of that? You could go system time. You count this thing. .0.027. Now, what if we do instead of doing that, we could go. We know that there's f is a sequence. What if you define that f is from 1 to this is 200,000. Now, what if you get some formulas? Fibonacci sequence. All right, that's what's the formula? Now, yeah, here it is. 1 divided by square root of 5. Let's just write it as a functions. Now we haven't introduced this, you to functions, but you could define it. Function function of in. Now it is equals to square root 5 times bracket seems to be 1 plus square root of 5 divided by 2. Now what do we get? To the power of n plus 1. Now this might not work faster. At least this could be a example of vectorization. Vectorization is some way when we write code that we could avoid using for loops. Now we run this Fibonacci sequence. Now I want fib of f. What do we get? It's got to be a pretty large number. But anyway, what is the time? System time fib f 0.017. Now what do we get for using for loops? 0.027. Here's the difference. So for some kind of efficiency reasons, we should use this kind of vectorized form instead of using for loop all of the time. And also it looks more elegant and it looks cleaner than this big chunk of code, like a noodle. Right. Now similarly, if you want to divide something by something, here's one of the actually more clever way. Now let's just vectorize the sequence of division term by term. Here we go. Vectorize the sequence of term by term. Now imagine you get f is originally 120, and we just name f. We just transfer f to the Fibonacci of f, and we get, not surprisingly, and we want division. Now instead of doing division term by term, we consider a list of number divided by another list of number with corresponding positions. What we could do is to use the exclude index, which is a minus sign plus another list of indexes. For example, I want to exclude the first term of the sequence. Now it gives all of the sequence except the first one. I want to divide it by all except the last one. Now let's just one sequence. If you divide it by itself, you get a list of 1. But if you exclude the first term and you divide by the list of number, exclude the last term, you get correspondingly the next term divided by first term. Now to prove that I'm not lying, that's also what I get. 2 divided by 1 is 2. 3 divided by 2, and then everything works fine. And how many times that takes? Okay. System time. I mean, you don't have to really have to worry about time in most cases, but as your algorithm gets more and more complicated, well, that doesn't make any sense because the time it takes is too small that it's a zero. And but it's a way of vectorization. And similarly, if you want to take the difference, there's two ways you could do this. Div f, that's the difference. Or you could go f is through the first one minus correspondingly the actually the other way around, I think. No, that's the same thing. Right. Pretty good. Now here's what we got for for loops and while loops. Why they're bad, how do we avoid them? And also you could go recursive function, which is not which we're not gonna discuss today. Now we have to introduce this to you. Judgment. And its term is if statement or Boolean vectors, actually Boolean variable, you can't put a list of Boolean vectors here. You can't put a vector of Boolean vectors here. If you do that, you always use the first term of it. And similarly, this bracket, statement, just statement, like do something, and statement 2, I'm not gonna repeat that. Now we get f, which is this sequence. Now we get a difference of f. You could go, well, actually I want the division of it. Division. Where is it? That's it. Right. I gotta name it D. Yeah. And you could use for loop. I want to see which of the term is larger than 0, larger than the golden ratio, which one is smaller. So you could go just equal on. There's nothing interesting about it. Wait, keep the format. Equal on if just go J is the vector 19. Right. Okay. Mode. Oh, it doesn't matter. We don't have to declare J. You don't really have to declare these variables unless there are some specific things you want to do with it. Right. If D term I is larger than 0, or it's larger or equal to 0, no, the golden ratio. Almost forgot that. Where is it? No. Yeah. Well, actually, we could use search instead of this. If di is larger or equals to this, we get J I is true. else equal else if some statement and other thing, but if there's just one case of it, you go else. Pretty simple. J I is false. Now we use capital T and F for Boolean variable, and I want to return J after this. Oh, do have to declare it? Usually, doesn't matter. Okay, that's numeric. You could actually go J is a numeric vector with length of 19, and then assign them to Boolean vectors. And true is just one. Or you could go something called can I do this as logical? J, yeah, choose false, nice. And also we can vectorize it. I think for some reasons, actually, not only programmers but also some designers like to use vectorization. It's not only because they can do parallel computing with it, which enhance the speed and power of calculation, but also it makes the code turns out to be elegant and turns out to be really simple. Now the vectorized thing is called if-else. If-else statement, and if it's true, do something. If it's false, do something. Or you could just leave it blank if you don't want it to do anything. Right. Now I'm gonna use J2 20 and what else? What else do we want to do? Well, better too. I think it's kind of annoying. Okay, J2 is if else D is larger or equal to this thing. Then if it's true, I return true. If it's false, I return false. J2, what is J2? Nice. Or you could even go L if else D is larger or equal D is larger or equal to, and then J. Can I do this? T J2. Well, this is gonna be different. Oh, okay. Evals J2 assign J2 to T, assign J2 to F. Their statement. Now, well, okay. Now what is J2? J2 is false. So here's the problem. If you want to assign corresponding element to corresponding places, you should go this way, because your output is a vector. If you just want to judge for each places and you don't want them to assign something to other things, because what happened is that the J2 turned out to be a vector with one element instead of 19 elements after this argument, because you could just you could just read like a for loop if this one is larger than this one, but what is larger? It's not all larger, so and the answer turned out to be false. But here's the problem: you you want to get 19 elements instead of just one element here. If you really want to just view it, go this way. TF, and yeah. So that's different way of using if-else. Actually, there are also things you could do with it. Same as for loops, same as if, else, if, lots of things. If d is larger than that, we plot it. Right? Otherwise, we don't plot. Now, want to plot something d. Let's just do one d. What's gonna happen? The length is different. So you should go is true. This one, just go J2 is 2. How many? Okay. J2. Where is J2? True, false. Is J2. We could go seek 1 J2. That's probably not the best way of doing this, but it's one of the fastest way. 10. So I repeat. Repeat 1 by 10. Okay. So I probably just end this video here. So see you in